Last time we talked about the ideal. Last time we talked about the ideal gas law and how it only functions at certain temperature and pressure ranges. So today we'll talk about what happens with real gases when gases don't behave like ideal gases, and some other properties of gases. So first up, let's talk about how the ideal gas law breaks down at these two categories: low temperatures, high pressures. And the reason for that is at high temperatures, they basically just act like billiard balls bouncing off of each other. If you remember when we talked about ideal gases, the conditions for them, all of the energy needs to be preserved for kinetic molecular theory in collisions. So they should be completely elastic. At lower temperatures, when they go by each other, they start to curve and bend because intermolecular forces start to happen. At high pressures, same thing. They're jam-packed in so close to each other that intermolecular forces start to interfere. They no longer behave with what we needed for kinetic theory. So let's look at some graphs of what should happen versus what we actually see with gases when they're submitted under these temperatures. So we'll have TA is bigger than TB. So the temperature of each of these gets lower as we go down, which you'll see as I draw. So we'll have our first line here. This will be temperature range A. And what we notice is that as we get to super high pressures, it actually breaks off of what we would see if we were using the ideal gas law to predict it. Remember that P and V are inversely proportional. So it starts to break off and go steeper. If we look at B, what we'll see here is that it kind of flattens and goes out. Where, hold on, I have that flipped. This is what the solid line is a real gas, and the dashed line is what we would predict. So we would see something like that. Here would be B. At temperature range C, you notice they kind of flatten out. We're not getting the nice smooth curves that we would predict. And in region D, that's what we would expect to see. Down here, this is called the liquid vapor region. And that's basically when your pressure is low enough that the line between what is a liquid and a gas starts to get fuzzy. So it definitely doesn't behave like an ideal gas then. Next thing we're going to do is draw a phase diagram. And a phase diagram basically just shows where a substance is in what state of matter. So we'll have our liquid phase up here. We'll have our vapor and the fuzzy line over to where it becomes a gas. They're kind of the same idea. Vapor is basically just, if you've ever seen steam come off water, it's just a little more dense air. And then solid over there. Let's use water for this since water is something we deal with every day. Down here on the x-axis, we'll have our temperature. On the y-axis, we'll have our pressure. I'll make this 0 degrees there. I'll put 100 degrees here. And right here we have 374 degrees Celsius. On this side, we will put our pressure. This is 0.0001 atmospheres. Let's look. We will have right here 1 atmosphere. And lastly, we will have up here, at that point, we will have 218 atmospheres. The reason these numbers seem arbitrary, but they're there for a purpose, and they are to demonstrate these properties. The first one is the critical point. This is the high energy point where it's hard to tell the difference between a liquid and a gas. Gases are moving around so quickly that they almost behave like a liquid, and liquids are moving so quickly they almost behave like a gas. Is the point where your density of your gas is approximately equal to the density of your liquid. So where do we see this on our graph? It's here. You notice I don't continue the line between liquid and gas beyond that, even though I do solid up here. The reason for that is because the difference between them becomes insignificant. So up there, that is what we call our critical point. It's when you get to a high enough temperature and pressure that you can no longer tell the difference between thank you, Bell, tell the difference between a liquid and a gas. The next one we have is the triple point. And this is where your substance is in all three, I know there are more, states of matter. Your normal states of matter that you talk about in like second and third grade. So on our chart here, this would be our triple point. So at this point, just a gentle nudge in any direction will shift it all the way into one of the states of matter. If I drop the pressure, it'll turn into a vapor. If I decrease the temperature, it'll turn into a solid. If I give it a little bit of energy, it's going to turn into a liquid. Cool? And yeah, one of the cool things about this is that water in space actually has no liquid state. That's why you don't see liquid water in space. So when you go out, because you're warm enough, the first thing that happens to you when you go out into space with no spacesuit is all of the moisture in your body violently evaporates. So you have an extreme burp and fart, and like all of the gas in your, like liquid in your eyes evaporates, and then you just kind of float out there. And after a while, you'll cool off and then turn into an icicle with any water that's contained in your body. Not a fun way to go. So let's talk about this next part here. And that is when gas, we call it a gas, when the temperature is above the boiling point. And we call it a vapor when the temperature is below the boiling point. Now, what is the boiling point? It's specifically for one atmosphere, so it's when we do it on Earth. That's why here, vapor, there, gas, boiling point of water is 100 degrees Celsius. Cool beans. Next, let's talk about when we do a phase transition. So 24, we have what's called condensation. And condensation, how much room do I have? Nice. Condensation is when low energy particles in a distribution collect and turn into a liquid. So remember when we talked about the Boltzmann distribution? These low energy ones are all going to collect onto a surface and they're going to turn into a liquid. So low energy particles collect and turn into liquid. And the opposite of condensation would be evaporation. And that's when we're taking the high energy particles off of this end. So high energy particles, still got room. It's when your high energy particles escape and turn into a liquid. This is how, into a gas, my apologies. Technically it would be a vapor at body temperature, but we'll just say it's a gas. So what we do is when we're running, we're heating up our body. Thank you again, Bell. We're heating up our body, and when we do that, we're shifting our distribution right until some of the particles have enough energy that they turn into a gas. Well, a gas isn't going to stick to us anymore. So now the highest energy of our particles have left, meaning the average energy of our particles is lower, meaning our temperature is lower. So that's how we cool off. An interesting thing about how we cool off, though, is that most animals can only do it through breathing and then the evaporation on their tongue. So the way that a lot of humans hunt down animals back in the day, we would literally just go at a moderate, like slightly faster than walking pace, and that animal's way faster than us, but we can track it. So we just keep going after it. The animal, and it would literally cook itself alive because it couldn't get heat out fast enough and stay in front of us. If you ever watch a cheetah, they can go real fast, but they can't do it for very long because they don't have efficient cooling. I'm going to erase these. Evaporate. Okay, those were both 24. Good. Now we're on 25. So for 25, we'll talk about boiling, which is different than this one. For boiling, boiling is when gases form in a heated liquid and leave when their pressure equals the surrounding pressure. So you guys may have noticed if you've ever boiled water before, you get little bubbles on the bottom. And basically all that is, you're getting those gas bubbles to form, and they won't leave until their pressure equals that of the air. We have two ones remaining, number 26 and 27. And for those ones, we'll talk about relative humidity. You guys may have noticed this on the news when they're talking about the weather. Relative humidity is basically just the percent of water the air can hold. The air is holding over what it can hold. So air at a given temperature has some propensity to hold water. The higher the temperature, the more air it can hold. The more water it can hold. You drop the temperature, eventually it has to lose some of that water. And we see that either as rain or during the night. Sometimes you'll see it as condensation, like the dew on the ground when you wake up in the morning. That's what happens when the temperature drops so low that we go below the dew point and the water comes out of the air. And finally, the last thing we have is diffusion. Last property of a gas we'll go over. And diffusion is just mixing substances due to Brownian motion. Which we had already talked about. Cool. The last thing, this is not part of the notes, but just if you go straight from a solid to a vapor, that's what's called sublimation. Just be aware of it. If there's not enough pressure, you can go directly from a solid to a gas. And that'll be it for this section on notes.